Okay, so we're diving into something pretty big today. It's all about the limits of those transformer models that everyone's talking about, right? You sent over some interesting research, especially that paper by David Chong, and it gets into this whole thing about circuit complexity.
Yeah, it's kind of like we're trying to understand the engine of these AI models. Not just what they can do, but what they're fundamentally capable of. What are the building blocks, the logic behind them?
It's like figuring out, I don't know, if a race car is built for speed or if it can handle a long race, right? And the research we're looking at here really focuses on this thing called TC0. What exactly is TC0 all about?
Well, TC0 is like a level of computational power. It's like having a basic set of tools for calculations and logic. And researchers have been trying to figure out if these transformers can basically use more advanced tools or if they're stuck with just this basic set.
Okay, so I remember reading that earlier research said that two common types of transformers, AHATs and SMATs, seem to fit into this TC0 category. But there was this idea that they were assuming limited precision, right? Like the models were working with rounded numbers or something.
Exactly. And that's where Chang's paper comes in. He asks, what if we remove that limitation? What if we give these models unlimited precision? Can they break free from TC0 then?
So what's the verdict? Do they?
Nope, they don't. What Zhang proves is that even with this unlimited precision, or even with a little bit of error allowed, both AHATs and SMACs are still stuck in TC0.
Wow. Well, no matter how much we try to boost them, there's this hard limit they can't get past. That's a little unsettling.
It definitely makes you rethink things. There's a whole bunch of problems that need more power than TC0 allows, and it seems like transformers, at least the way we know them now, just can't solve those problems.
Okay, so before we get too deep into that, can we just back up for a second? I need a little reminder. What are AHATs and SMATs again? I know it has something to do with how these models focus their attention, right?
Right, so think of them as different ways of focusing. SMATs use this thing called softmax to calculate attention weights, turning scores into probabilities. Basically, they're spreading their attention based on these probabilities.
Okay, so they're kind of weighing different parts of the input differently. What about the AHATs?
AHATs are much more picky. They only pay attention to the absolute highest scoring positions. Like, imagine a spotlight shining only on the most important words in a sentence.
Interesting. So even with these different ways of focusing, they both hit that TC0 limit?
That's right. And Chang doesn't just say it, he actually proves it mathematically for both types.
All right, you've got me curious. Tell me more about these proofs. What's so special about them?
Well, for AHATs, Chang's technique is pretty clever. He takes rational numbers, fractions, and represents them as pairs of integers. And by doing that, he shows that all the math these models do stays within the limits of TC0, even when those fractions are super precise.
So it's like he found a way to look inside the model and show that even with these infinitely precise fractions, they're still playing by the TC0 rules.
Exactly. Now with SMATs, it's a bit trickier because they use the softmax function, which involves things like exponents and square roots.
Ah, yeah, those sound a bit more complex.
They are, but what Chang does is he breaks down each step of the SMAT calculations and shows that even those more complex operations can still be done within the limits of TC0. And he does this while allowing for a much higher level of precision than what previous research looked at. He moved from logarithmic to polynomial precision.
Okay, so even with a big boost in precision, they're still stuck. So what does this actually mean? Does it mean there are some tasks that they just can't do?
That's one of the big takeaways. If a task needs more power than TC0 allows, then it looks like transformers just can't solve it, no matter how much precision we give them.
That's pretty huge. Are there any examples of those kinds of tasks?
Chong actually mentions one in the paper, figuring out if a Boolean formula is true, those logical statements with and or and not. Turns out, determining if they're true needs a level of logic that's beyond what TC0 can handle.
So even though we see transformers doing amazing things with language, they might struggle with really complex reasoning or understanding the nuances of logic.
That's the point. And what's even more interesting is that Chong talks about these exact SMATs. These are SMATs that make decisions with a little bit of a safety margin, a tolerance for error.
A safety margin, what does that mean in this case?
It's like giving the model a little wiggle room in its calculations.
Okay, so even with this wiggle room, are they still stuck in TC0?
They are. Chung proves that even if we allow a tiny, tiny amount of error in the final answer, these exact SMATs are still limited by TC0. It's a whole new way of looking at the limits of these models.
This is getting really fascinating. We're actually starting to see the boundaries of what these models can do, even with all these tweaks and adjustments. I'm definitely ready to dig deeper into what this means for AI.
Definitely. And there's a lot more to unpack. This whole thing about TC0, it really makes you think about all the hype around AI. It's easy to get excited about all the new stuff, but we have to understand what's really going on under the hood.
Yeah, it's like being amazed by a magic trick. You're impressed, but do you really get how it works?
Right. And Chung's research is like saying, hey, let's look deeper. Let's not just be impressed by the results. Let's see what's really happening inside these models. Just because a transformer can create cool images or write nice text doesn't mean it truly understands what it's doing.
So how do we get from those impressive results to dealing with these limitations? Can we go beyond TCOVA, or are we just stuck?
Well, there are some hints in Chung's paper. Remember we talked about those exact SMATs, the ones with a margin for error?
Yeah, the ones that were still limited by TCO, even with that flexibility.
Right, and that gives us an idea. Maybe we don't need to break free from TC0 completely. Maybe we can find ways to work within those limits but still tackle complex stuff.
So instead of trying to build a spaceship with just basic hand tools, we figure out how to create something just as amazing using those same tools.
Exactly. It's like maybe we break down those big complex tasks into smaller chunks that fit within the limits of TC0.
Like building something incredible with Legos, but you only have a limited set of blocks.
That's a good way to put it. And this could lead to new ways of thinking about AI. By understanding the limitations, we can design things that work around them, even if it means staying within boundaries.
So limitations can actually lead to more creativity. By knowing what we can't do, we might find new and interesting ways to do what we want. Earlier, you mentioned paper and how it describes the regular languages that AHATs recognize. Can you explain that a bit more? What are these regular languages and why is that important?
Think of regular languages as like a set of rules for patterns and grammar. How symbols are arranged. They're used everywhere from programming languages to analyzing DNA.
So they're like the fundamental building blocks for how we represent information.
Exactly. And Chang's work creates a map that shows us which of these building blocks, these regular languages, AHATs can work with and which ones they can't. Some fit neatly within TC0, so AHATs handle them no problem, but others belong to a different category called NC1. And unless there's a huge breakthrough in complexity theory, those are off limits for transformers.
So it's not just about saying, here's the limits. It's also giving us direction for future research. Now we know which language patterns work with current transformers and which ones need us to come up with something new.
Yeah, that's key. Instead of just trying to build bigger and more powerful models, we can focus on designing ones that can handle those languages that are currently out of reach, those in NC1.
This brings us back to being realistic about AI. We need to celebrate how far we've come, but also understand where the limits are, and then use that to push things further.
It's all about balance, excitement, and also critical thinking.
All this talk about complexity in languages might sound a little abstract to people who aren't deep into AI. So what's the main takeaway for the average person?
I'd say the big thing to remember is that AI, especially these transformer models, is still pretty new. We're still learning about what it can do and what it can't.
It's like we've discovered a new continent, but we've only explored the coastline.
Exactly. As we explore further, we're going to find amazing things, but also some big challenges. This TC theater research is one part of the map, and it shows us how much more there is to discover.
So even though there are limitations, there's still so much so much potential. This has been a really insightful conversation. Ready to wrap things up with some final thoughts?
Yeah, let's bring it all together.
Okay, so we've gone pretty deep into transformers and complexity and limits. What are the big takeaways here for our listeners?
Well, one thing that's clear is that even though transformer models have done some amazing things, they're not a magic bullet. They're really good at certain things like understanding language, but when it comes to raw computing power, there are some hard limits.
Right, it's like we've been so focused on how fast this race car can go that we forgot to check if it can handle off-roading.
That's a perfect analogy. And this TC0 thing, it's like a speed limit for transformers. It tells us what kind of problems they can solve quickly and efficiently.
And what's really interesting is that this speed limit seems to be there no matter what we do. We give them unlimited precision, we let them have some wiggle room, and they're still stuck.
Yep. Chung's research really points to the idea that there are some fundamental limits built into how transformers work, and we can't just easily get around them by tweaking a few things.
So are we just stuck then? Are these limitations permanent?
Not necessarily. I think this research shows us where we need to go next. Instead of trying to force transformers to do things they might not be good at, we can focus on creating new type of AI that can handle those things.
So it's like realizing that our current tools, even though they're pretty amazing, might not be enough to build the future of AI. We need to invent new tools, right?
Exactly. One way is to explore totally different architectures, ones that aren't limited by TC0. Another is to find clever ways to break down those really complex problems into smaller steps that fit within the limits.
So instead of building a whole skyscraper with just a hammer and nails, we figure out how to do it in smaller, simpler stages that we can manage with what we have.
That's the idea. We need to work smarter, not just harder. And by understanding these limitations, we can focus on creating creating better solutions.
And it comes back to being critical, right? We can be excited about AI, but we also need to understand what it can't do.
Definitely. It's about finding that balance.
So for everyone listening, next time you hear about some amazing new AI thing, remember this conversation. Think about the limits and how we might get past them.
Because that's how we keep pushing forward. We learn about the constraints, and then we find creative ways to break through them.
This has been a great deep dive. We've covered a lot, the power of transformers, the whole circuit complexity thing, and what the future might hold for AI. Oh, our listeners got something to share. Let's hear it.
Please remind me what's next level for the TC0.
That's an interesting thing to bring up, and it touches on something we haven't talked about directly, but it's relevant.
Yeah, it seems like you're bringing in an analogy about security and limitations, right?
Yeah.
Like how things that seem very impressive might still have vulnerabilities or restrictions.
Exactly. In the paper, it talks about these transformers doing some very complex math, but it turns out there's this underlying limit, TC0, that they can't break free of.
It's kind of like how a security system might seem impenetrable, but still has a critical flaw that someone could exploit. Or even just the fact that no matter what security measure is taken, there's always some limitation to it, right?
Precisely. And that's where the reminder you brought up about things not always being what they seem fits into our discussion of AI.
So even the most advanced AI might have those hidden vulnerabilities that we need to be aware of. Okay, let's bring it all together. We've covered a lot of the power of transformers, the whole circuit complexity thing, and what the future might hold for AI.
Well, one thing that's clear is that even though transformer models have done some amazing things, they're not a magic bullet, you know? They're really good at certain things, like understanding language. But when it comes to raw computing power, there are some hard limits.
Right, it's like we've been so focused on how fast this race car can go that we forgot to check if it can handle off-roading, right?
That's a perfect analogy. And this TC0 thing, it's like a speed limit for transformers. It tells us what kind of problems they can solve quickly and efficiently.
And what's really interesting is that this speed limit seems to be there no matter what we do. We give them unlimited precision, we let them have wiggle room, and they're still stuck.
Yep. Chong's research really points to the idea there are some fundamental limits built into how transformers work, and we can't just easily get around them by tweaking a few things.
So are we just stuck then? Are these limitations permanent?
Not necessarily. I think this research shows us where we need to go next. Instead of trying to force transformers to do things they might not be good at, we can focus on creating new types of AI that can handle those things.
So it's like realizing that our current tools, even though they're pretty amazing, might not be enough to build the future of AI. We need to invent new tools, right?
Exactly. One way is to explore totally different architectures, ones that aren't limited by TC0. Another is to find clever ways to break down those really complex problems into smaller steps that fit within the limits.
So instead of building a whole skyscraper with just a hammer and nails, figure out how to do it in smaller, simpler stages that we can manage with what we have.
That's the idea. We need to work smarter, not just harder. And by understanding these limitations, we can focus on creating better solutions.
And it comes back to being critical, right? We can be excited about AI, but we also need to understand what it can't do.
Definitely. It's about finding that balance.
So for everyone listening, next time you hear about some amazing new AI thing, remember this conversation. Think about the limits and how we might get past them.
Because that's how we keep pushing forward. We learn about the and then we find creative ways to break through them.
This has been a great deep dive. We've covered a lot, the power of transformers, the whole circuit complexity thing, and what the future might hold for AI.
Until next time, keep exploring, keep asking those tough questions.
And keep diving deep, and always remember that things are always what they seem. Thanks for that, listener.